Hello everyone. So today we're going to go over section 7.3, modeling data using exponential functions. First, this instruction right here was for the old TI-83s that we used to use in class. So we will not be using this today. Instead, we're going to be using the Desmos graphing calculator, just like with the polynomial functions from the last chapter. Okay, let's look at some examples. We can see example 1. It is a Simon, a biologist, is investigating a new bacteria culture that could help strengthen a person's immune system. There are 50 cells at the beginning, and then the cell's growth is tracked over a period of 5 hours, once an hour. His results is in the table below and on the graph on the right as well. So you can see that not only is the graph increasing, the rate of increase is also increasing as time goes on. So we can see that this is a exponential model, mainly because the scatter plot looks exponential. Okay. And as we move on to other examples, sometimes it would not look the case. But for this one, it's pretty clear that it's going to be exponential. Okay, here it says use regression to determine the exponential function that best model the data. We're going to use round the a and b values to 3 decimal places. So the exponential functions that we're looking at all have the form y equals a times b to the x power. So that's what it means for a and b, to be rounded to 3 decimal places. Okay, so let's go to the Desmos graphing calculator. And you can see the numbers has been plotted here on the left already. We have 0 through to 5, and then on the right hand side, the number of bacteria at each time. And the graph looks exponential. As you can see, the just like what we had on the page as well. Okay, so we're going to go ahead and type in the regression formula. We have y1 tilde a b and then to the power of x1. Okay, so in this case, the numbers were specifically chosen to match a exponential function that was like pre-produced. So we are going to have a high r value. In fact, r squared is equal to 1. Again, that's a little bit beyond the scope of this course. And then it says here the parameters are for a is 49.892. We're going to 8925. We're going to round that up. So it's going to be 49.893, and then the b value is 1.50. Sorry, 1.501 if we round it correctly. So let's go back. So yeah, so we have y equals to 49.8, sorry, 893, rounding up. And then the b value will be 1.501, and then to the x power. All right, so again, if you're just looking to see what should be put into your calculator or your Desmos window, it would be y1 tilde a b, and then the power button x1. Okay, once you have the a and b values, then we can use this exponential function to determine the number of bacteria. In this case, when in the 8th hour. So we'll simply have x equals 8, and then we're going to find out what the corresponding y value is going to be in our function. Okay, let's go ahead and do that. Punch in a line here. X equals 8. Okay, so the intersect is beyond the graph, so we're going to start moving it and find the intersection. and we do, it looks like it'll be 1,285 bacteria. Right, it's 1,284.57, but we'll round up to 1,285 bacteria. Okay, so one thing that you will notice already is that because the exponential function increases faster as time goes on, sometimes you're going to have to change the window in order to find the intersections that you're looking for. Okay, let's look at another example. One that will be quite familiar to us is about compound interest. So here it says Angela invests $2,000 in GICs that increase in value every 3 months. So that will be compounded quarterly. The table below shows the value of the investment during the first 18 months. We're going to use exponential function to model the data, and it's going to be, because it's compound interest, we already know it has to form y equals a times b to the x power. Okay, so let's look at this. Again, already typed in for us. Notice that the graph almost looks like a straight line just because the interest rate is really low. So you're not going to get that exponential growth until a little bit later. Well, you still get exponential growth, but it's a little bit harder to see until the numbers get a little bit larger. So in this case, again, same thing. So we have y1 tilde a b to the x1. Yeah, so again, these numbers were chosen specifically for this question, so r squared is going to be very high. The parameter a is actually exactly 2,000, so that's good, and the b value is going to be 1.002. So we can just go ahead and record those. So y equals 2,000, and then 1.002 to the x power. And then says in part B, determine the value of the investment after 2 years. So this means x is going to be equal to 24 because the variable was in terms of months. Okay, so x is 24, then y, oh sorry. If x is equal to 24, then y is going to be equal to, let's see here. Okay, x equals 24. That would be $2,098.04. Make sure to include units, so $, $2,098.04. Okay. Next one, again, similar kind of idea. Now, notice that these are the x variable is years, and is recorded 1900, 1912, and so forth. In order to keep our coefficient small, we're going to write this since 1900. So that will give us a new set of x values, so 0, 12, 28, 36, 60, 72, and 84. A little bit more manageable. Again, we're going to produce a regression first. Let's see here. Again, has been plotted for us already. Notice that it's decreasing, which makes sense. Over time, the athletic performance for marathoners are going to get better, so it's going to decrease the time. So let's see here. Again, y1 tilde a b to the x1 power. R squared is a little bit lower this time. It's not quite as high, which makes sense because this is something that we took from, like, this is actual historical data. But still, it's very usable for us. We have an a value of 171.939, which is pretty close to 180, which makes sense for us, although that is the one point that is most out of place. And then b is going to be 0.996. All right, so let's record that. Y equals 171.939, and then 0.996 to the x power. Now, which makes sense because it is exponentially decreasing, and exponentially decreasing function has a base that's between 0 and 1. So 0.996 is less than 1, so that works. And then we're going to use this to estimated winning times in 2 different years, 1924, so x is going to be 24 in that case, and then also in 1952, so x is going to be 52 in that case. All right, so we're going to find the corresponding y values. Okay, let's see here. Let's go back. So we have x equals 24, gives us 157 minutes. And then on the other hand, if we change the x values to 52, we will get 141 minutes. Okay. Finally, the last one, same kind of thing. Population of town over 50 years is the population is increasing. It looks pretty exponential if you just look at how fast the numbers are growing. We can use the regression once again. So let's see here. Again, the data is already plugged in. Year 1, 11, 21, 31, 41, 51, and then the population as stated in the question. So again, y1 tilde a b to the x1 power. All right, so a value is 10,854, and the b value is 1.059. Okay, but if you round it up, there will be 1.060. Okay, so let's go ahead, record those. And then it says after 35 years. So if the first, it's a little bit confusing how it's written. I believe when I made the question, I meant to ask x is 36. So this is 35 years after year 1. Okay, so x is 36. Let's see what y is equal to in that case. Okay, so here, simply make x equals 36. And the intersect gives us a population of 87,500. All right, so that's it. So a few interesting ideas here, particularly the one about compound interest. It goes back to when we learned about financial mathematics at the beginning of the semester. So that was good. And just very similar to what we did in the last chapter about polynomial functions and their regressions. So as long as you know the form and enter the data accurately, it should be pretty straightforward. But that's all I have for today. Thank you for listening.